Hey everybody, Dr. Rachel Valletta here, environmental scientist with TFI, with another fun little afternoon here at Franklin at Home. Today we're going to be talking about a publication that came out and coverage of that publication just last week on something called the Arctic methane bomb. You may have heard about this before. Periodically, every few months, this worry comes up. And it's certainly something to keep our eye on, but often it is overblown. So I thought today we could jump on coverage of that paper, talk about why it may or may not be very useful for us, and then get to the heart of the matter, what lies at the center of that methane bomb concern, and it is something called permafrost. So before we get into that description, let's just give a really high-level overview of this publication. You may have seen coverage of it in some science news media outlets, including all the way up through USA News. We saw that perhaps climate change is, quote, past the point of no return. Let's just cut that off at the knees right now. That is not the case, folks. Climate change is not past the point of no return. Why do the authors of this publication make such a strong claim? Well, it's all based on a simplified model that they use. Now, the type of model that they use is called an Earth systems model, and there are a number of leading Earth systems models across the globe that we use to basically simulate or try to mimic how the natural environment actually interacts between the atmosphere, the land, and the ocean. This is what we use to help us understand temperature projections when we're talking about our changing climate. This particular model, as I mentioned, is rather oversimplified, and the big claim that a lot of news coverage leaned into, again, that idea of being past the point of no return, is all based on this one finding, and it is as follows. If humans were to stop all carbon emissions today, right now in the year 2020, this simplified model finds that warming would continue unabated, and that we're already past a tipping point having to do with permafrost. Now, again, this model is oversimplified. That claim doesn't stack up against all of the other leading Earth systems models that are out there. Okay, so we don't have to worry about this particular claim. If you saw that circulating, you can take a deep breath. But it does turn out that carbon emissions from this particular source are still a concern. So let's gear ourselves with some information about permafrost so that the next time you hear about the idea of an Arctic bomb or an Arctic carbon bomb, Arctic methane bomb is another term that's used, you'll know what it's actually referring to and where the truth may or may not lie. All right? Okay, we're good to go here. So let's jump right into our description of what permafrost actually is. Now, permafrost is what's called perennially frozen ground. So that means that it is soil and rock and sediments that's frozen or below 0 degrees Celsius for more than 2 years at a time. And importantly, it has an upper layer and a lower layer. So let's go ahead and draw that out right now on my handy dandy whiteboard. All right, permafrost is mostly found in either high elevation areas, such as mountainous regions, or it can be found across tundra regions in the extreme northern latitudes. We also find some features of this in the southern hemisphere. Okay, permafrost layers can be just a few meters deep, up to a few kilometers deep. Okay, so it can be quite an extreme feature. Now, I mentioned it has an upper and a lower layer. So let's imagine here that we're looking at a transect of the ground. So I'm going to put some grasses here. So if you can see my color there, I'm going to put some green coloration. And just to get a sense of what we're looking at here, I'm going to draw a tree there. I'm going to come back and talk about that tree, why it may or may not be there in reality, but just so you can acclimate yourselves. Okay, so the upper layer of this permafrost, this permanently frozen ground, is what's called the active layer. Alrighty? It's important that we understand the distinction between the active layer and the lower lying permafrost, which is down here. That's my dog sharing in the excitement about permafrost. That's okay, Rowdy, I feel it too. Okay, why are we talking about that upper active layer? That upper couple meters of permafrost features undergoes seasonal thaw and refreezing, okay? So even in the coldest areas of, let's say, the Canadian tundra, the Alaskan tundra, we still have some minor thawing in the uppermost portion of that soil. Okay, that's called our active layer. The portion that doesn't undergo seasonal thaw and refreeze is that permafrost layer. That's that permanently frozen ground that's beneath our active layer. Alrighty, so far so good, pretty straightforward, right? But why do we talk about permafrost in the context of climate change? Well, it all has to do with what's locked up in that permanently frozen ground. Now, up on top here, you'll notice I've used that green marker to indicate plant life. Over time, over millennia in fact, plant life in these cold regions dies off, but it doesn't decompose. In fact, we need warmer temperatures for that decomposition to proceed. So that seasonal thaw that happens in the active layer is actually really important to help start to decompose dead plant matter, or you may hear me say organic matter. Organic matter can be dead plant matter and dead animal matter, as well. And it all contains carbon. When that material dies off in the upper layers of the soil, it sort of just sticks around. It may decompose partially, it may not. If it's in that permanently frozen layer, microbes won't help with that decomposition. So we don't actually ever lose any of the carbon that was in that dead organic material. Alrighty, but in the context of climate change, as temperatures warm up, as that thaw season becomes longer and that active layer becomes more active, essentially, we can have more of the carbon that's released down in my permanently frozen layer. Here's how that works. Over time, as temperatures warm up, we can actually see that the active layer gets deeper and deeper. I'm going to change my marker color here so you can see that a little bit better. There we go. Over time, my active layer begins to get deeper and deeper as we have warming temperatures. Alrighty? So as the temperature in the atmosphere, let's go ahead and show that by a T, increases in the air, so increasing temperatures, that leads to more thawing of the active layer, continued decomposition of that permafrost layer, which leads eventually to what? To more carbon gas release. Okay? So, temperatures in the atmosphere increase. We have further degradation and decomposition of that permafrost layer, the organic material that's rich down there. From that decomposition, we have release of carbon. It can be in the form of carbon dioxide or CO2, which we often hear about in the news, or it can be in the form of methane. Methane is CH4. Alrighty, these are two very powerful greenhouse gases, methane in particular. And what do? Ultimately, they increase the temperature of the atmosphere. Okay, so we've completed our cycle here. Let's go over it one more time. As temperatures increase in the atmosphere, the permafrost regions of the world begin to warm up. As that warming continues, we have a guest star here. I'm worried about warming too, buddy, no worries. As that warming proceeds, we have more thawing of our permafrost layer. As that thaw continues, microbes begin to decompose the carbon-bearing plants and organic matter that's locked up in that frozen layer. As that decomposition continues, carbon-bearing gases like carbon dioxide and methane are released, ultimately leading to increased temperatures in the atmosphere. Okay, this loop is something that we call a positive feedback loop. Alrighty, so I'm going to go ahead and I'm going to put a big plus sign right in the middle there. Now, this is what's at the crux of understanding what the methane bomb or the Arctic carbon bomb is. It's this idea of a positive feedback loop. Now, that publication that I mentioned that came out last week, it's in the journal Scientific Reports. It is open source. You can read it for yourself. Scientific Reports is the journal. They claim that we're already locked in to this runaway system, this idea of this positive feedback loop, whereby each step amplifies the next. But it's just not the case. Now, the reality of the situation, and most other Earth systems models do accurately depict this, the reality of the situation is that we are having some carbon release from these thawing permafrost layers, but it's not leading, we're not yet locked into this runaway system. Now, this runaway system, as I mentioned, can be called a positive feedback loop. It also represents a climate tipping point. I'm going to write that phrase down also, because if you follow along with climate news, you may have heard about it also. So I'm going to plop this down at the bottom here. It's called a climate tipping point. Alrighty? Climate tipping point. And there are a few crucial climate tipping points that we have to keep our eyes on across the globe. You may have heard of other very, very pressing, very worrisome tipping points. Now, tipping points, you can kind of think about the analogy of being on a seesaw in the kids' playground. The tipping point would be the point at which we're each sitting on one side of the seesaw, and if we're equally weighted, we're going to balance each other out. But if someone is much, much heavier than the other person, they're going to sink the seesaw, aren't they? And there's no way for that lighter person to sort of flip the seesaw back, okay? They've passed that tipping point. They're in an irreversible state. That's exactly what's going on in climate tipping points. Those tipping points represent periods at which the climate system enters into a fundamentally new state, i.e. an irreversible state. Some other notable climate tipping points include concerns over the loss of irreversible ice sheets. So that climate tipping point, let me say that one last time a little bit more clearly. Other tipping points include the potential irreversible loss of the Greenland ice sheet and the West Antarctic ice sheet, which we're keeping a close eye on. And again, we're also not yet locked in to those systems, though we do expect to see some continued loss. All right. So in addition to greenhouse gas release from permafrost, we also want to make sure that we know it's problematic for the communities that live in this area. As permafrost begins to thaw out, it goes from that frozen solid ground to fairly muddy, fairly unstable ground. That unstable ground can ultimately upset the way humans and the way animals feed. It can create or take away lake features, changing their entire ecologies. It can also impact human infrastructure, for example, roads, perhaps gas pipelines. In fact, we've seen degraded gas pipelines that ultimately can lead to leaks thanks to thawing out permafrost. All right, so it's a problem not just for the atmosphere, but also for the everyday lifestyle of the folks and the animals that live up in this area. Alrighty, so those are the basics that I have for the notion of permafrost as a climate tipping point. Feel free to drop any Q&A into the comments, and my team back here is going to help pass that along to me. But while they're doing that, there was one final point that I did want to hone in on, and it's that permafrosts, it's one additional feature of what the Arctic methane bomb might actually be referring to. I've spoken about permafrosts here as they represent soils, as soils represent permafrost, but we can also actually have subsea permafrost. Now, this is related to something you may have heard called methane ice, or methane clathrates, gas hydrates. These are all sort of the same, referring to the same thing, and what it's referring to is this crystalline structure that contains methane. Okay, it's essentially an ice form of methane, that really, really worrisome other greenhouse gas that I've written in the top right here. Now, methane can be locked up within those methane hydrate ice-like features, and there is another concern that warming will lead to methane hydrates entering into a similar positive feedback loop, passing another potential climate tipping point. These particular features are found in the subsea regions, primarily in the Siberian region, actually. We have a large abundance of these. And there is concern that as oceans warm up, we'll see continued degradation, continued melting, essentially, of that methane ice. But that also is not yet something that we're seeing of grave concern. So if you've heard about the Arctic methane bomb coming from methane ice, that also is overwrought, that worry. There's two basic reasons that we think that we're not really going to see a lock-in to that loss of methane from methane ice anytime soon. The first is that right now, if we go out to the oceans, we can actually measure methane that is relatively new versus methane that's been locked up in those ice features for some time. We do that by radiocarbon dating the methane gas and the carbon it contains within the ocean. When we go out to these sites and we do that radiocarbon dating, we find that we're not seeing really, really old methane released into the ocean water column. So that would seem to suggest then that we're not having degradation of these methane ice features. Okay, so that's one reason that we feel pretty confident we're not yet locked into loss of those methane hydrates. Second reason is simple thermodynamics. So in those methane ice features, when the ice goes from a solid to a liquid, it's what's called an endothermic reaction. Okay, that sounds kind of complicated, but let's break it down. Endothermic as opposed to exothermic, meaning that when the ice goes from a solid to a liquid, when it melts out, it actually takes in heat rather than releasing heat. So we're not locked into this positive runaway feedback cycle whereby melting of the methane hydrates releases methane into the water column, creates more warming, creates higher temperatures, creates more melting, and so on and so forth. No, in fact, this is a negative feedback loop, which is the exact opposite of what we've described here, and it actually is a self-damping process whereby those increasing temperatures that lead to the melting of the methane hydrates in the first place are counteracted by the reaction of the methane hydrate going from a solid to a liquid. Okay, so there are some concerns that we're seeing some steady loss of carbon emissions, both from those subsea methane hydrates, that methane ice, and from on-land permafrost. And we'll get to some of the differences in why those estimates in just a moment. We do have a question though. The question is, why are scientists so concerned if we're not actually seeing degradation? So this is perfect timing. Thank you for that awesome question. Scientists are concerned because we are in fact seeing some carbon from permafrosts, and the amount of carbon that's stored in permafrosts is gargantuan. And it could be, now hold on to your hats here because this is a pretty extraordinary number, and I think some folks aren't ready for it. The estimate is that permafrosts across the globe contain as much as 2 times the amount of carbon that is already in the atmosphere. Okay, that's double the amount of carbon that's already in the atmosphere. So you can imagine then that the warming potential from the potential release of carbon dioxide and methane from permafrost could be extraordinary. If all of that were to release overnight, we'd see fundamental shifts in our climate system, extraordinary warming trends that human civilization almost certainly could not adapt to. Luckily, that is not the case. That's not what's happening. Some of the projections for how much carbon could be released into the atmosphere over the next few decades come from the IPCC report. That's the Intergovernmental Panel on Climate Change report. And those values, I'm just going to pull them up because I want to make sure I get them absolutely bang on for you. They could be anywhere between, let me pull up that stat again for you. Hold on just 2 seconds. Okay, there we go. I have that in front of me now. We could be talking about on the order of 1 to tens of gigatons of carbon from permafrost over the next few decades to upwards of hundreds of gigatons of carbon. Okay, now that order of magnitude difference, it's kind of challenging to figure out, right? But basically what that translates into is we could be seeing degradation of just a few percentage points of permafrost carbon stores to a few tens of, upwards of 60, 70, 80, maybe even 90% of the carbon stores locked into permafrost by the end of the century. These are extraordinarily different values. Why do they differ so drastically? There's a couple reasons for this, and it has to do with how we actually measure the carbon that's locked up in permafrost. So we can go about this in a couple of different ways. One way is through field-based research. Field-based research means a scientist can go out to visit a permafrost site, can collect samples, and can make an estimate of the amount of carbon dioxide and methane that's currently being released, and try and extrapolate how much carbon is in the permafrost at that site, both vertically, and horizontally, so across a large spatial extent. Okay, now those estimates for carbon stores could differ with satellite measurements. Okay, so we can do field-based measurements or we can do satellite-based measurements. You can imagine that satellite-based measurements might be preferred because they're much, much easier. They can get across a wide swath of land in the way that individual field parties cannot. But we find that those measurements of active carbon release from permafrost are actually not very well resolved. It means that we're not getting a good handle on the amount of carbon that's being released that the field studies seem to suggest we're seeing. So what's the problem here? There is a mismatch between field measurements and satellite measurements. Again, it probably has to do with the resolution of the satellite measurements itself. It might just not be fine enough. Or on the flip side, our field measurements could be biasing those areas that are losing the most carbon gas right now. Okay, so I think that's the long and the short of it here. We wanted to keep it short and sweet for you because this is a pretty complex feature that we actually just went through. This is something that I might lecture to a university course. So congrats for staying in with us here today. So let's just do one last review of why folks are focusing in on permafrosts. So remember, permafrosts cross the northern hemisphere. They make up about 25% of the northern hemisphere land coverage, and they contain upwards of 2 times as much carbon that's already in the atmosphere is contained in permafrost. It could be the case that we lock ourselves into a positive feedback loop whereby continued warming leads to continued degradation, continued thawing and decomposition of the carbon stores locked within that permafrost. That degradation can lead ultimately to more greenhouse gas release like carbon dioxide and methane. We're especially worried about methane. And that in turn can increase temperatures. We are not locked into this system yet though, okay? So if that is the case, we should then maybe turn our focus to something that's a little bit more urgent. And it looks like we just had that question come through in the chat. Thanks again. What should we focus our attention on then that's more urgent? Well, I keep bringing up that methane in particular is a concern. All right, methane, CH4. CH4 stands for 1 carbon atom, 4 hydrogen atoms. Methane is very, very effective at trapping atmospheric heat. Okay? It's much more effective, it turns out, than carbon dioxide is in the short term. Over a period of 100 years, methane is upwards of almost 30 times more powerful at warming the atmosphere than is carbon dioxide. So when I say we're especially worried about methane, that's exactly why. It has a much higher what's called global warming potential. It has the potential to warm the atmosphere much, much more than carbon dioxide does. So it stands to reason then that we should be focusing in specifically on those sources of methane from human emissions. So we know right now, of course, that burning fossil fuels releases carbon-bearing gases. Carbon dioxide is the biggie we talk about. Methane is outsized warming. So where can we focus in on that? Well, there's two big things here. One is in the agricultural sector. You may have heard about this before. We often talk about cows, right? So cows are indeed a major source of methane. And it doesn't have to do with just their flatulence, actually. Mostly that methane comes from cow burps, which is quite interesting. So cows have, they can partially decompose their lunch in their stomachs, and they can release that gas in the form of methane. So it turns out that, yeah, the amount of I have another dog visitor here today. The amount of cattle that are grazing across the globe right now turn out to be a really, really substantial contributor to global methane emissions. Okay, so agricultural sector and specifically cattle can be a big source of methane. The other big source of methane from human systems can come from decay within our landfills. And this primarily comes from decaying organic materials. The same exact process that's happening in these frozen or now thawing permafrost layers can happen in our landfills, whereby organic matter, particularly wasted foods, decompose and release an outsized amount of methane in our landfills. So this is often why folks say if you'd like to take up a climate-friendly practice, you can take up composting, for example. So keeping that methane all within one contained area, reusing it in new soils, for example. Another big source of methane that we haven't quite quantified, but we are on the hot pursuit of is leak of methane from natural gas pipelines. This, of course, is a major concern here in the state of Pennsylvania. There's a couple big studies going on, in part with partnerships between some federal government agencies and the EDF, the Environmental Defense Fund. They've recently launched a methane monitoring satellite that is honed in on places like Pennsylvania, trying to truly identify where methane emissions are coming from. Just one moment here. Buddy, I'll take that. Again, my dog followers are very jazzed today, so we'll wrap up here, I think, in just a moment. But again, identifying where those methane leakages are coming from in those natural gas pipelines is really, really crucial. It's very challenging to measure methane in these buried or partially buried pipelines in rural parts of the state. And it's likely that there's many more leaks that we're unable to sort of observe and do those field-based measurements on than we can do with satellite imagery. So there you go. So two, and added a third in, major methane contributor from human activity. So from cattle certainly is a biggie, from food decomposition in our landfills, and certainly leakage from natural gas pipelines. Alrighty, we're coming up on the half-hour mark, so I think I'll pause us here, folks. Now you know you are defended against any kind of misinformation that may come out against around the Arctic methane bomb. If you see it pop up every few months, as I say, very reliably it does, it is very, very, very unlikely that there will be a sudden bomb, a sudden release of methane and carbon dioxide emissions from frozen permafrost soils, whether they be above ground or in the subsea environment in the Arctic region anytime soon. And rebuting the major claim from that Scientific Reports article just last week, no, we are not yet locked in to that positive feedback loop. There is still time to lower temperatures to avoid this system from setting off. So of course that means then delimiting the amount of fossil fuel emissions and carbon-bearing gases from those fossil fuels as soon and as aggressively as possible. So that'll do it for us. I will see you next in mid-December, and hopefully then we'll be having a special programming turning our attention from the northern latitudes to something a little bit more Philly-centric, and it may or may not have to do with the dreaded spotted lanternfly. So hang in for that, and we'll see you again in a few weeks. Stay safe, and happy holidays.